Hey Mo, how you doing?
How you doing?
Pretty well. How about yourself?
Very good, very good. How's everything with you?
Going well. So yeah, give me a quick update on our progress.
Yeah, actually, is I start printing. I don't know if you can see or not. If you come close, this,
Yeah.
but it's not finished yet. I don't. Something happened so it's clogged inside the. So the printer start building inside, um, melting the filaments, but the filaments go around the injection area and build like molting. I have pieces here.
What type of filament are you using?
PLA.
Okay. And what nozzle size are you using? Using 0.6 or zero point 0.4?
We're supposed to be going six, but I'm now in the I'm now in the mood of the having just updating the frames.
Yeah, because when you change nozzles, you have to recalibrate your printer.
Yeah, that's what I'm doing now, right?
Yeah, so
Yeah,
you can print a calibration cube to see how far off your printer is, and if your printer has auto leveling, you can redo that again.
yeah.
Um, so that's probably the problem you're running into. And then when you go to print, since our things are very small, you might want to try increasing the infill level. That might help. Can you pull up a our full image? I want
Sure.
to see what
Yeah,
how
yeah,
far you progressed, because I
yeah.
had a few notes I thought of last night about the spinning mechanism.
So,
Okay, so okay, I see your problem. So I would print these flat side down.
but if
I
you
think
if you did that when you come in the top, if you come in here in one side to fill it, is no room to go on top of it to make a holes. You got my points? So if we go sliding, I'll show you. So
what are the holes diameter?
see, you see this one here. The good thing is you go build it piece by piece. Let me go zoom in. Think about the one have a holes. If you this one is appropriate to build it, but when you have it aside, how you can do this piece inside here. So let me go
Oh,
back.
I see. I see your problem. If so, I would add supports because remember the ones that don't have holes need to be completely filled. The more
Yeah,
filled they are, the stronger they work when it's actually metal. For plastic, it doesn't really matter because this is just an example.
yeah,
For
yeah.
the
Yeah, go
for
ahead.
the holes, whenever there space in between the holes, that can be filled with support.
Yeah,
So that
I can do that, but if you print it with this with vertically like that, it doesn't need support.
okay. Yeah, because like I have a dual IDEX printer that can print supports in water soluble material. That's what we'll be printing for the metal stuff. This plastic is just for the test. So just this is to see if there's any like small tweaks we need to make these work better. Like if we need to make them slightly thicker or make the circles slightly bigger. This is what this test is for. Um, so
So
uh,
this part here, this part.
so what? Yeah, what problem are you running into?
I have no problem now. Just only I'm looking for like the starship. So if the starship complete, I'll be fine. I'll be in the
Okay,
ship.
yeah. What I can you zoom in on this current diagram you have right now?
So let me go open the
Oh
main.
yeah, open everything so we can see it all together. Okay, so uh,
So this
so
one here, we fix this one. I'll go overview with you.
yeah, let's go over everything you've
Yeah.
changed.
So we changed this one here. First of all, I did remodel it, not remodel it, assembly back again in order to have a motion. So
Uh-huh.
so this
Did you make the electromagnets thicker too,
yeah.
or did you just elongate them?
No, this one is
Can you
thicker
can you
and
give me a
longer.
top overview, a bird's eye view
Yeah.
of the C-shaped electromagnets? and then directly overhead.
Direct overhead. Okay.
Yeah, and zoom in on it crossing over. Okay, so yeah, that should be fine. What's the current diameter? Oh, this is before you've scaled it down too, right?
No, not scale it yet. I'll go scale it
Okay,
later.
so okay, here's something to think about. If you go back to okay, stop right here and zoom in on the outer hull, the top part that connects to the C-shaped electromagnets. So if you scroll up a little bit, the central capacitor.
Center
Sorry.
class of this one.
Yeah, so you see how it's
You talk about
you
this
have
one?
a lot more material than you would necessarily need for this for the outer hull. And because as we shrink everything down, we want to maximize as much as we can for the coils. Remember, the rotor coil is going to be on top of here. So and everything has to fit inside that 4.6-inch sphere, right? So everything, if you can shrink down this outer hull, the top part and the bottom part, so it uses less material and it's a simpler design, and you can fit a bigger coil. Because remember, the middle part is going to be this whole thing, and then there's going to be a coil on top and a coil on bottom. And if you can,
Where's the coil on top, coil on bottom? There's only
oh,
one.
I'm talking about the Rodin coil and the Starship coil. So right now the Rodin coil is
Okay.
on the wrong side.
Yeah, the top, yes. Okay.
Yeah, surround, and then the
Excuse me, 1 second.
dodecahedron.
This one 14 side. This okay or have to be 12?
It has to be 12. Yeah, it's a very particular geometry. It has to do with higher level dimensional geometry.
Okay. All right.
It's very but what I'm saying is that the outer hull you can shrink a little bit. So this will be on, so that move the Rodin coil to the top, and the Starship coil will be where the Rodin coil is right now, right? Does this make sense?
Yeah, this the Starship will be here, right?
Yeah, and the no, the Rodin coil will be there. The Starship coil will be where the Rodin coil is right now. Make sense?
No.
So okay, move the Rodin coil up.
Hold on a second. Can use a mouse?
Yeah, so
Yeah, let me go give you permission to use a mouse so you can.
okay.
How you do this? I remember how we do it. Where you go more and more, share screen, share sound, share meeting, leave the meeting.
Here, I can just, so where you have the Rodin,
remote.
okay, where you have the coil right now, right? It just needs to be in the opposite place. So currently it's on the bottom. We need it on the top.
This one?
Yes.
Okay.
So that needs to go on top.
Okay. Let me see here. Simple, easy.
Yeah, perfect. Okay. And what's going to happen is right now, this Rodin coil, if you zoom in the Rodin coil and the outer hull, like right where they meet.
Yes.
So zoom in right where they meet. The Rodin coil and the outer hull.
This Rodin coil, right?
Yeah. And the outer hull is that other thing. So zoom in right where they meet. So see how there's extra zoom in more, like try to get a different angle if you can. And then give me a different angle so I can show you. So you see how there's extra. Okay, yeah. So right where the C-shaped magnets end.
Yes.
And it connects to the central capacitor. You see how there's some dead space there? You could shrink that down so the Rodin coil can take more space, because what happens is if you throw in a quick 4.6-inch diameter sphere, you'll see that the everything's going to shrink a fair amount. And so we want the Rodin coil as thick as possible. So you can maximize the surface area if you shrink that outer hull a little bit where it meets the central capacitor. So and then remember, the dodecahedron goes in the center of the Rodin coil, the 12-sided one, where the have a top side pentagon, have an opening mechanism so we can like fit stuff in it. Make sense?
Yeah, but here 1 second. You see this one here?
Oh, okay, perfect. Here's a better angle. So you can see where you can shave off some of the here I made a diagram. Yeah, you can just, that part, you can just directly connect it closer to the central capacitor. so you can steal more space for the rodent coil. You see what
You
I'm talking
want
about?
like
So
okay,
so right now
you
it goes
wanna
to, yeah,
you want to this one let me go back here 1 second here. So
yeah.
do you want to we go inside here more by because the angle here is can help you to go inside more.
Yeah, you could just slope the angle more and get rid of all the extra material, because you really don't need that much extra material. And it would create more surface area for the rodent coil. Because remember, the rodent, how you have it now is perfect where the rodent coil is lined up. But when we shrink everything into the 4.6-inch diameter, like, can you throw in a? It's probably easier. So yeah, can you draw a line from the edge of the C-shaped electromagnet straight to the central capacitor?
Straight line. Hold on.
No. Right where your red arrows are now. You can just. Yeah, I wish I could do this for here.
Yeah.
Let me just
Try to get the remote control.
okay.
Auto share. Yeah, share clipboard. Yeah, go ahead.
So right now,
You can have control in the mouse, I think.
am I controlling your mouse right now?
Yeah, I think you can. Oh, give I am.
Oh, here we go. All right, can you see my mouse?
Yes.
Okay, so this is what I'm talking about. So right here, that can go straight more at an angle, and that can get rid of all this extra material, and you can like slim it down, like right here.
Okay.
And the straighter you can get it, or you can make it a curved design, whatever's easier to print, you'll find because the less support material, the better. But see, if by doing that, you shave off all this extra bit, and you can make this diameter smaller. And what happens is the dodecahedron is going to be like right in the center, right here, right?
Yes.
So this is where the dodecahedron is, and the top pentagon is going to face up, and we're going to be able to have a opening mechanism to remove it, so we can add powder into it, right? So this gray mechanism spins counterclockwise, and this green mechanism spins clockwise, right? You understand this, right?
Say again one more time. What's the green one?
Okay, so the green one is this whole central capacitor.
Yes.
With all of these octahedrons on it, right? This is the entire green mechanism that spins clockwise, and then this gray mechanism with all these red C-shaped electromagnets spin the opposite way. So there's two spinning mechanisms, and then these outer octahedrons also spin independently while they're spinning.
Okay, so let me hold on a second here. 1 second.
So
I want to show you here. 1 second.
Yeah.
So,
can you throw in a 4.6-inch sphere that's like 4 millimeters thick?
Yes.
Because if you scale everything down now, we'll know what things we have to fix. Because all these test prints don't really mean anything if we're gonna have to scale them down.
So here what's happening. So this guy.
So that one spins one, yeah.
And this then guy turn, but how you connected the wires while this turn?
So the wires are should be kind of like circuit breakers, where every time they pass through either the blue octahedrons or the orange capacitor plates, every time the circuit breaks, and that's how it goes from high voltage to low voltage, and it goes boom, 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 boom. So something, and that's like how we give that pulse type voltage. Remember, in simplest terms, how does this device work? It's asymmetric capacitors with pulsed high voltage, and this pulse, boom, 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 is giving the pulsed high voltage. These are all asymmetric capacitors with the central asymmetric capacitor, and it's just pulsing the voltage back and forth, and all of this. These electromagnets pulse, the central capacitor pulses, and all it's doing is passing the energy back and forth. And these giant coils on the top and bottom are extra capacitance and pass the energy through inductance, just like your, a wireless cell phone charger passes it by having the same resonant coil where it can pass the energy back and forth, or how a giant Tesla coil can charge wirelessly from like a few meters away. That it's all the same thing. Does this make sense?
Yes. No. I just look. You were too smart. You're too smart. So I'll go.
Okay. So
I follow you. I'll follow whatever you tell me. All
So
right.
it helps if you understand the technology, right? Because you're
I, I'm
designing
I'm
it.
I'm
So
going.
there's a science journal that explains more of the physics and equations that you can here. Can you get back to the design? I'm not
Sure.
familiar with SolidWorks. Okay.
Yeah.
Can you throw in a 4.6-inch sphere
Sure.
and
Sure.
just have this into the design from now on, because this will keep your parameters in set, because we will
Yes.
use a sphere for this initial
Yes. How
iteration.
4.6.
4.6-inch diameter sphere. I'd say let's do 4 millimeters for now, or 6 millimeter thickness, whatever works.
4.6 inches, right?
Yeah, diameter, and
Okay.
then make it 4 millimeters thick.
4 4.6 inch, which is so small.
Yeah, see, this is gonna clarify things, because now when you go to do those test prints, you know exactly how much thickness you have to work with.
Yeah, but
So
you cannot having. If I go, I
so
I push
yeah.
too much. I push too hard to maintain the 2 millimeter and the
Okay,
6
yeah.
millimeter.
So
But
here's what I'm thinking right now. Go ahead and let's just look at it, right? So go ahead and make the sphere 4 millimeters thick. Okay.
the sphere of this,
Yeah. Make that 4 millimeters thick.
sure. 1 second.
And
Yeah,
we'll just do all the design inside this parameter from now on.
1 millimeter. See.
Okay. Now in the very center of the sphere, make this hole. Can you see my mouse still?
Yeah, go ahead.
Okay. So in the center of the sphere, make this whole gray, with the capacitors inside it, slightly further away from the wall so it can spin freely. So scale that down so it fits directly in the center of the sphere.
Yeah, with the coil, without coil, without this coil.
Everything. We'll do the coil second, but this one first.
Okay, all right.
Because then
So
I'll show you what I meant about the surface area for the coil
sure,
after
we
this.
can scale everything now.
So yeah, select all, scale it all inside that sphere, and then we'll see what kind of thickness we're working with. And then we can start labeling which materials which. That will clarify things too, so you know better how this works.
Let me save this guy first.
Okay.
And save as quality scale. Um, let's see. Mm, mm.
Yeah, is there a way to select all and scale it all at once?
Yeah, so this one here.
It just needs to be slightly smaller than the internals of the sphere so it can spin freely. So like, like a few millimeter differential or whatever.
Let me see here. 1 second.
Yeah, because the current diameter is what, 5.3 you said?
Uh,
So we need to scale it down by what, 25%?
yeah. Remember that? Yeah, 25. Yeah, around 25% to 20%. Yes.
Okay. Yeah, so let's scale it down to 25% and see what kind of thickness we're dealing with.
Because with that dimension, I compact, as you see, is a compacting very hard. Okay, and
Yeah, because this is our limitations right now. This
I'm
is
saying
the
is
max we can do.
yeah, but if you the point is I have 2 millimeter, I stack on top of shuttle. Second, yes.
Did your computer freeze? I know it's a lot of RAM to
Yeah,
process.
yeah. Um, no, it's once having an issue with combine all this together.
Yeah.
But definitely I will. Anyhow, we're gonna get the concept so far. Let me go see something quickly here. I'll go exit that.
Yeah, because what we need to do is scale everything inside the sphere,
Yeah,
and then we know what kind of thickness we're dealing with, and then that's when you want to test the plastic prints based on that new design. Because right now you're testing it on a design that's going to be too big for what's going to fit in our final.
I understand, but like I
Yeah.
said, you can see from design is very compact and is very do like and I have no room, like it's not room enough
Yeah,
for everything. And
if
still
everything's 2 millimeters right now, right?
two
And
millimeter
we
and
and
sometimes some of them 3 millimeters.
okay, yeah. Let's say a 2 is the smallest thing, right?
Yes,
So let's say everything's 2 millimeter and we shrink it by 25%. That means everything's going to be 1.5 millimeter, which is okay because that means on a 0.6 millimeter nozzle, it will be able to go at least 2 times in a.
yes.
So that's okay. That's why I told you make everything 2 millimeter thick now, because I knew we were going to scale down. It probably would have helped if we started off at the scaled down version, this so it wouldn't make your computer crash. But you might have to do like half of it and then do the other half. If it's not going to let you, or do it externally. You
I'm go see if I can scale. Let me see here if I can scale them all together one shot.
Yeah, let's try to do this now so we don't have to do it later.
Yeah. That's what I'm trying to do it. Try to have it all of them one shot.
If not, we'll have to do them separately if your computer can't handle the
Yeah, the model has become big and big now. So we go 25%.
Yeah, so would it be 0.75? Or
Uh,
you're scaling it down 25%. So yeah, it would be 0.75, right?
I go see. We'll go see both 75. That's mean 25% left off. Let me see.
Did it work?
Yeah, as well.
Okay, can you throw in the sphere again? See if it fits inside there now.
That's what we're going to do it now.
And then we'll save this so we don't have to deal with this again.
I know you want to make sure your scale is correct. See,
Yeah, just throw in the sphere, the one we already made.
yeah.
Save that as part of the file now, because the sphere is now part of the design. So sphere is 4.6 inches diameter, and then it's 4 millimeters thick.
That's good. 4.6.
So yeah, we're gonna have to shrink it a little bit more.
Yeah, a little bit more. Yeah. All right. And so we can go 70%. Let me see here.
Wait, put in the sphere thickness first, so we know.
Yeah.
Because then all you have to do is
4 millimeter inside or outside?
It doesn't matter.
Okay.
Oh, the max thickness is 4.6 inch. So inside. Sorry.
Side.
Yeah.
Okay.
Okay, so save that as part of the file. Okay, now what is the current diameter inside the sphere with a little bit of space? And then that's how we know what equation we need to use for scaling down.
So just we're looking for
the very center of the sphere to the other side, the diameter with, let's say, 2 millimeter differential.
So you talk about
inner sphere to inner sphere.
Inner sphere to inner sphere. We have 7 millimeter. We want to put the stuff inside. From you can see from the screen here. This one.
We're 7 millimeters off.
If you have the wires off outside.
Okay. What if you round the wires around the C shape and they don't stick out?
Exactly. We can do that. So we can see here. So this is good point.
Can you fix that right now and just cut that out?
And no, I can't immediately. So we talk about 0.67 millimeter difference between the frame to the 0.
So we need to shrink it another what, 5%?
No, the 0.6 even doesn't come 1 millimeter. So maybe let me go.
Because remember, it also needs a spin inside the sphere as well. So there needs to be a little bit of space. Let's say like 2 or 3 millimeters space, because it's going to shrink. It's going to shrink in the kiln. So we want to make sure everything works right. So yeah, let's say 2 millimeters on each side. So let's scale down to 0.73. Let's try that.
Okay. Let me see here. 0.73. Yeah, 0.73 maybe it's work. Yeah, let me see.
And then just save all the files at this level so you know what to do in the future. How far off is it still?
Yeah, this will be saved. Yeah, I already saved here.
Okay, cool.
This one already saved.
And just work inside these parameters from now on so we know what we're missing.
Yeah, so
because you're gonna have to change some of the design so it works again.
Try 70. We'll try 70.
70? Okay.
Yeah, I'll go 70, see how it goes.
Yeah, you'll steal some space when you fix the coil, but like we want everything inside it.
Yeah, okay. 70.
Let's try that.
And weird.
Does that work?
But no too much room left. Yeah.
You're gonna have to adjust the coils.
Yeah, this how maybe we can have to. Yeah, I have to readjust it back again here because this one, whatever we do, does not move enough. Hold on a second. You see, yeah, it's outside already. This guy here, which is a maximum outside the rings, the rings should be this guy move inside.
Yeah.
So something wrong here for misalignment. I'll go fix that. But yeah, that one here. Let me go. We want to see.
Is everything inside the sphere now?
Yeah, everything inside the sphere now. But we want to see the thickness.
Yeah.
See the thickness now. The thickness, the most important thing. These guys. Yeah. We want to see.
Oh yeah, each layer.
Yeah, each layer here. Everything is moved wide because we have
you'll just have to make slight adjustments to fix everything.
Yeah, we can work precision, more precision in this here. We do something quickly, so it's not. Let me see thickness, the most important thickness here. Thickness from here.
What is it in millimeters?
Yeah, millimeter now. 1.73 millimeter.
Okay, that's fine. Can you check the spark gaps of the outer octahedrons real quick.
The
So
spark
of the blue ones. What's the
Yeah.
thickness of those?
Sure.
Because as long as those meet the requirements too, we're good place.
Okay. Let me see.
And then you can just re-uniform everything after in this new dimension.
Yeah. And just so I want to make sure everything is fine with this. Let me see here.
So it looks like we lost the spark gaps. You might have to remake those.
Yeah.
What are the current layers?
Yeah,
just do a layer. Yeah.
The layer is the most important thing here.
Oop.
Okay, so we want to.
Yeah, just do that one.
Well, okay. So do that. Wow, man. 1.37.
Okay, that's within a reasonable dimensions. Okay.
Okay.
Can you throw the sphere back in there?
Sure.
And just from now on do everything with the sphere in it so you know your limits.
Okay. So the sphere is here already. But
yeah.
I have to remodel.
Yeah, you'll have to
reassemble it nicely.
And you can get rid of the points of the coils, just have it uniform around the electromagnet.
Yes.
And you can steal can you see my mouse still?
No, try again.
How about now?
Yeah, I can see it now.
Okay, so and you're gonna want to, you can shrink this part on both sides to where it's closer to this green.
Sure.
So that way you can have a big rodent coil here and a big rodent coil underneath. Are you inside the sphere right now? Is this the sphere?
Yes.
Okay, so yeah, so you'll want one. You want the rodent coil, the coil you already made right here. Make it as big as you can inside the sphere, of course.
Okay.
But you want to scale this outer hull first to see how much room you have to work with. Okay.
Okay.
And then same thing with the starship coil down here. And then the dodecahedron goes right here, the 12-sided pentagon, with the top pentagon facing upwards right here. And then down below, you know the spinning mechanism, how it's like that glass syringe design?
Yes, you showed me before.
Down below, so the rodent coil has the dodecahedron in the center, but down below the starship coil will have this tip. Can you zoom in on this tip?
Sure.
Okay, see how that tip is like cylindrical?
Yes.
So this will expand slightly past the starship coil center. The center, if you look at a starship coil, the center is open. So this will pass straight down and then a little bit past the starship coil, still inside the sphere, of course. Because what will happen is, we'll have, can you see me real quick?
Yeah, hold on a second.
Okay.
Yeah. Okay.
So what will happen is the sphere will open up, and when it's upside down, the starship coil, that little cylindrical tube I was talking about that goes slightly above the coil.
Yes.
Are you still following me? That will be like a top that will spin manually to get it started, because it does need so we'll spin it up while I counter rotate the outer hull. So if they're spinning counter rotating, then I close the sphere. And if we did all the equations, all the math right, it should reach a resonant frequency inside that sphere cavity. And that will be able to carry not only its own weight, but a few pounds past that point to carry cube satellites. Does this make sense?
It does make sense. So it's a good point. So
okay, so yeah,
one
so
side is bigger than another.
No, they're all uniform, but one side has the dodecahedron, the other side just has a longer cylindrical tube for spinning. Okay, imagine like a dreidel or a top.
Yeah,
right?
yeah, it's something.
Something so it's easy for us to spin to start it up.
Yeah,
and then a benefit of that too is the magnetic field. The entire central capacitor now goes through the coil, the starship coil. Remember how the dodecahedron, rodent coil, and starship coil are also capacitors. And remember, how we tap into that energy? Through inductance. So we need to make sure everything in between can access that energy, just like your phone has a little coil and it connects to another coil that's equal size and it can pass the energy back and forth. The same thing goes for the rodent coil and starship coil, passing the energy to the central capacitor. Make sense?
Okay. Makes sense. Yeah.
Okay, so after you just fix all the uniform scaling we just talked about, keep the sphere, make sure everything fits inside the sphere, fix the outer hole so you can add more space for the rodent coil. Of course, you still need to make the starship coil.
The point was here after I finish it. I finish with your meeting now. I go reorganize everything back again and scale it up in the main models, and we go from there.
Yeah,
And
perfect.
I
And
will
then
go. I will go Brent with a 0.6 millimeter nozzle.
yeah, and keep
Yes,
everything and everything you print from now on, make sure it's that smaller model where it's inside the sphere. Okay.
No print the. Can I
No more
print
printing the bigger stuff. Everything has to fit inside that sphere. So that's the only stuff you're going to test, because that will then translate to when we actually print in metal. Make sense?
Makes sense. Yes. Okay.
Okay, so if you have any more questions, just rewatch this. The last 5 minutes will probably have most of the details. So there's three main things. You're fixing all the uniform scaling. You still have to make the starship coil, and then you'll shrink the outer hull and add that little cylindrical tube. Okay.
Okay. All right. That's good.
Okay. That can you get all that done in the next day or so?
Yeah, I'm working on it today.
Okay, perfect.
It's not as I didn't think is. I think now we are almost. I mean, we made the major topics, major things, and it's only try and error for printing, and we made the starship coil.
Right. Remember, this is just the first iteration. And we're just trying to get everything that can print properly. We'll test it. The first iteration might work flawlessly if we get all the equations and math right. If not, we'll make another iteration. But the whole point of this is, if we follow all the math correctly, we'll get a functional design that can actually carry its own weight and a little bit more weight past that and lift.
How much weight you planning for?
Minimum, we need a few pounds, but if we do everything right, and we really get good at it, I'm talking about like hundreds of thousands of volts. We could actually carry a human. But right now we're just aiming for 10 to 30,000 volts, so we can carry a little cube satellite. Okay.
All right.
That's our first step, because once we got this thing, yeah.
I don't know how can I say to you. I'm very excited to see the result.
Once we get this flying, sky's the limit, right?
Yeah. We'll see. I'm working with you here. We'll see what sounds good.
Okay, what I want you to do is whenever you're working on this, I want you to not only believe that it's possible that it will work, but believe that you already created it successfully. Can you do that for me?
Yes, I got it. I got it.
So whenever you're going to work on this, believe you've already succeeded. You're just going through it again, right? That'll keep you in the right mindset. That's what Tesla always did. He always had the right mindset for it.
Okay. All right. Okay.
All right, I'll talk to you soon, buddy.
Take care. Thank you. Take care. Bye.